De Broglie told us that the matter wave associated to a particle with linear momentum p has a wavelength given by Planck's constant over p. In this problem, we're going to explore the consequences of the wave properties of matter. Let's see the problem statement. I send a single electron at a time at a screen with two slits by accelerating the electrons from rest through a potential difference of 60 volts. The distance between the slits is 280 nanometers, which is much greater than the width of the slits, and the detection screen is 30 centimeters away from the screen with the slits. Where on the second screen are we least likely to observe each electron? Our detector will always measure discrete particles localized in space and time. We want to ask, what is the relative probability that a particle will arrive some distance y above the center of the screen? Now, experiments done with electrons, just like this one described in the problem, tell us that this probability is mathematically equivalent to finding the intensity profile of a wave whose wavelength is given by h over p, for p the linear momentum of the incident electron. Particles in quantum mechanics are described by complex numbers called wave functions, psi, say, of x. And the intensity profile of this wave, so the probability distribution that we're trying to compute for the electron, goes like the absolute value squared of the wave function, of the associated wave function to the particle. Now, this is just like in normal wave mechanics, where the amplitude of a wave is given by a complex number, and the intensity of the wave goes like the absolute value squared of that complex number. So in our setup here, the incident electron is described as a plane wave incident on the screen, and then it diffracts at the slits, and circular waves spread out from the slits. These waves interfere with each other, in some places constructively and in some places destructively. We've schematically sketched that pattern of constructive and destructive interference here. Now, importantly, if we call the wave function that comes out of this first slit psi1 and the wave function corresponding to the wave at the second slit psi2, then the total wave function is given by the superposition principle. Psi equals psi1 plus psi2. And the intensity profile for the wave associated to the electron goes like the absolute value squared of psi1 plus psi2, not their individual absolute value squareds. Okay, so what's the punchline? The punchline is that even though the electrons arrive in discrete particle-like lumps on the detection screen, the probability of where they're going to arrive is determined by the intensity profile of their associated wave function. We're told that the openings themselves are much smaller than the distance between the slits, d. So in other words, single slit diffraction effects are negligible, and we need to use the double slit diffraction pattern. Now, remember that for a double slit, the intensity profile is a sinusoid, schematically like this one that I've drawn. And what we want to compute are the minima of this sinusoid. So remember that for double slit diffraction, we expect destructive interference when the distance between hole 1 and the screen is different from the distance between hole 2 and the screen by an odd number of half wavelengths. So what this gives us, remember, is a formula, d sine theta min, so this is for minima in the pattern, equals m plus 1/2 lambda, where m is an integer, equals 0, 1, etc. So further, we know from the geometry how to relate the distance y to the length between the two screens. And this is tangent theta equals y over L. Okay, so now we need to compute the wavelength that appears in this formula. And we can get that by computing the momentum p of the electron from energy conservation. In particular, for an electron fired from rest and accelerated through a potential difference of 60 volts, by energy conservation, we have the initial energy is 0, and the final energy is the kinetic energy of the electron, plus the potential difference, which is minus E, the charge of the electron, times the 60 volts. So this is the voltage, which will plug in 60 volts. Of course, this velocity is related to the momentum P equals mv, and so from these formulas, plugging in the numbers, which see the attached PDF for more details, we would find that the wavelength of the electron is 1.6 times 10 to the minus 10 meters. Okay, so we're least likely to find the electron where the intensity pattern on the screen is at a minimum. So that's the y for which theta min satisfies this equation here. So we can write the equation for minima as, let's say, y min equals L tangent theta, theta min. So solving for theta min here, plugging in here, we would find sine inverse of m plus 1/2 lambda over d, the distance between the slits. Okay, so for instance, plugging in the numbers for m equals 0, the first minimum above the center, would give, so for instance, m equals 0, we would get y min equals 8.5 times 10 to the minus 3 centimeters. So that would be the first minimum above the center in this intensity pattern. Okay, so there are two things I want to emphasize here. The first is that all matter has an associated matter wave, but very massive objects have very small wavelengths. And so these interference patterns become very fine. For a macroscopic object, the distances between minima and maxima are so small that a detector of finite size would not be able to detect the interference pattern. The second thing to emphasize is that we found that for an electron incident on a slit, the probability of where it's going to be found on the screen is given by the intensity pattern of the interference pattern of the wave. Now, this is true even for a single electron incident on the double slit screen. In other words, the electron is not interfering with other electrons. It is truly interfering with itself.